Okay, Assalamualaikum and good morning. Today we will continue on the next topic, which is convection and radiation. So before this we will learn on conduction, which is heat transfer by using solid. Most of them are solid. Okay, so here we'll learn what is convection and radiation. So basically, convection is a mode of heat and radiation transfer between solid surface and adjacent liquids or gases that are in motion. So it could involve combinations of conduction and fluid motions. Basically, convection is when we have a hot block over here and we have a flow of air or fluid moving on the top of hot block. So we could name it as convections. So heat is being convected from the hot block towards the air or toward the fluid. Fluid could be gases and could be liquid. So that is fluid, right? The greater the fluid motion, the greater the convection of heat transfer. So, for example, when you are sitting in front of your fan, your body is heat because of your exercise. When you are speed up your fan, then you feel a bit cooler than before because of the fastest the fluid motion, the greater the heat is being convected from your body to the air. So you are removing heat faster. In absence of any bulk fluid motion, heat transfer between solid surface and adjacent liquid is purely conduction. So here, if for example this is T dot, there is no fluid motion, here we could say that this is conduction, but this is too detailed. So I just want you to assume that whatever is heat is being transferred from the solid towards fluid is convection. Okay, convection could be divided into two type of convection. The first one is we call it forced convection. We have fan over here, or it could be drawn by fan, pump, or wind. Okay? So the hot egg is being cooled by forced convection, which we have a fan or wind that blow the egg back. The heat of the egg remove faster compared to natural convections. Over here we have natural mean free convection, doesn't have any forces, doesn't have any winds, doesn't have any pumps. Why use pump? Because fluid could be liquid. So in liquid, to make it forced convection, we use pump. Okay? And then this is air. Air is mean naturally going up because the hot air is moved up compared to the cold air is moved down. Okay, then this egg is being naturally convection, naturally cold. Then here is the formula. You need to remember this one. This is, we call it Newton law of cooling. Why Newton law of cooling? Because Newton's makes this formulas. Okay? So Q convections, Q dots means that heat per second, joule per second. Joule per second is Q dot, or call it watt W. Okay? W is joule per second. Then is equal to H AS Ts minus T infinity. What is H? H is convection heat transfer coefficient. The units are W over meter squared degree Celsius. The next one is AS. What is AS? AS is surface area through which convection heat transfer takes place. So this surface area, we call this surface area, is on the top of the here the surface area is the eggshell. Yeah, surface area. Then we have surface temperature, Ts. So here, for example, Ts on the top of the temperature on the top of the shell. And then we have T infinity is temperature of the fluid sufficient far from the surface. For example, here we have T infinity is not too far, it's just above it. Okay? This is T infinity. So temperature of the fluid. So by having this formula, we could calculate Q convections. Okay, Q convection is also depends on the H. H is experimental, it also depend on the surface geometry, the nature of fluid motion, the property of the fluid, the bulk fluid velocity. So here you could see this is the value of H. If, for example, the free convection of gas, the value of H is from 2 up to 25. Free convection of liquid, the value is from 10 up to 1000. The forced convection of gases, 25 up to 250. Forced convection of liquid, 50 up to 20,000. Boiling and condensations from 2,500 up to 100,000. Okay. These men that make the formulas. Okay. Please read it. Okay, Newton law of cooling. Next one is radiation. What is radiation? Radiation is energy that emitted by matter in form of electromagnetic wave or photon as a result of the temperature change in the electronic configure of atoms or molecule. Actually, this radiation is come from the sun. Okay, with that doesn't require any medium. Okay? It's no medium at all. It doesn't require, but it also could radiate from a hot surface. For example, you stay in front of your car that being started. Your engine is moving, so you are sitting in front of it. So you could feel the hot of the car without touching it, without having the fan inside moving. So how that the heat being transferred to you? So that one is we could call it also radiation. Radiated without air, without any medium. Okay. But most of them we neglect. Because we always assume that radiation is always from the sun. So from the other material in the world, we assume it radiations. We ignore the value. Okay. How to calculate radiations? Here is we have a Q emits. Max is equal, means value of Q is at maximum, equal to sigma alpha s Ts. Alpha is Stefan-Boltzmann constant. This is constant value 5.67 times 10 to minus of 8 watt per meter square Kelvin to power 4. So this is the value of alpha. Okay, Stefan-Boltzmann constant. Time As is surface temperatures, Ts is temperature of the surface. So and then we have if this is maximum, but it's not on the real surface. So real surface we must times with emissivity, which is this epsilon emissivity. So we times the epsilon is equal to 1, means it is black body. Black body means it emits 100% of the everything is being transferred, is being emitted out. Whatever being transferred to the body, to the material, then it will transfer everything back. So here we have emissivity value. For example, we have aluminum foil. It could only emit 0.07. or we have here red brick. It could emit 0.95 up to 0.96 times whatever we have here. Okay, then we have absorptivity. Absorptivity is a fraction of radiation energy on the surface that is being absorbed by the surface. So it means that if absorptivity is equal to 1, means it being absorbed everything. And 0 means it's not absorb anything. So here we have a Kirchhoff law. The emissivity and absorptivity of a surface at a given temperature and given wavelength are equal. So we have here Q absorptivity is equal to alpha Q incident. Actually, this is when we have incident of sunlight. Q over here we have some being absorbed. So this is Q absorbed, but to find it how much we should be equal to times alpha times Q incident. So some is being reflected, so to find it we time alpha minus 1 times Q incident, so we could calculate the value of how much is being absorbed and how much is being reflected. Okay, then here we have another formula where is the net of heat transfer. Is the difference between the rate of radiated emitted by surface and radiation absorbed. So for a surface like this, for example, the formula is equal to epsilon times alpha times AS times the different temperature between Ts and T surface, and both we have to multiply by 4 to the power of 4 before we subtract. Okay, the next one this is Q combined. Okay, Q combined. Sometimes we could not find Q for convection only or Q for radiation only. So sometimes it's given that Q for radiation and convection is in 1 each. So we use this formula when we have a Q combined. When we have a H combined, so this is the formula for it. Okay. Stimulus heat transfer mechanism. Okay, stimulus. So here we have, for example, we have an opaque solid. This is means solid 100%. So it being conduction in 1 mode. Conduction 1 mode. Sometimes we could have gases like this. We could conduct by radiation and conduction or convection. This is 2 mode. And we have a vacuum only. We could only have radiation, mean transfer. No solid, no conduction at all. Okay. Problem solving technique. So here, for example, when we have a problems, this is a technique that being used in heat transfer. And actually, the first thing you should understand what are the problem are by understand the statement that been given. Second thing, you should draw a schematic. Whatever you have, for example, you just have a small figure of it. So you need to draw a schematic where the heat is being transferred from where to where. What are the thickness? What are the value of H or Q or any given formulas? Assumptions and approximation. For example, the formula state or the equation state ignore radiations, ignore convection, only conduction. Then the assumptions. And a physical law, does it involve convection? Does it involve radiations or only conduction? Properties, for example, the value of the value of K, thermal conductivity, the value of H, and calculate. And then we're reasoning and verify and discuss. Normally, in heat transfer, you should try to make at least 3 significant figures. 3 significant figures means that, for example, here this is 3 significant figures. 3.75, this is 3. 0.845, this is 3 significant figures. 1, 2, 3, 4. And this is if you times this one, 3 significant figure is 3.16. Find masses 3.16. So only 3 significant figure is equal to 3.17. Okay, this is example of thermal conductivity. So thermal conductivity. Yeah. Thermal conductivity inside what we have here, wire being heated, okay. And then we have a material on left, and on the right side we have E. So here you need to find what is the value of Q. This middle wire is being supplied by 35 watt. So it's being divided too, because the heat is supposed to be going there and here, going left and right. So 35 watts is being divided by 2 equal to 17.5 watts. Area is 0.1 times 0.1. This is being given actually. Okay. Area over here is equal to area over here. Okay. Where heat being transferred out. Different temperature means that this is should be T1 minus T2. Okay. 82 minus 75 equal to 8 degrees Celsius. Then by applying what we have here, applying towards these formulas, rearrange the value of K outside. So we could find the value of K, 1.09 watt per meter Celsius. Okay, the next one, heat transfer. Heat transfer steadily to the boiling water in the pan at the bottom, the inner of the surface of the pan, given temperature of the outside to be. It means, so here for example we have a thickness of 0.4. 0.4. What we have here, 0.4 cm or mm. Okay, and then we have temperature of the inner is 105, and we have this 800ths of what? 800 watts. So the first one, find thermal conductivity. Aluminium is K equal to 2.37 watt per meter degree Celsius, and we find the E equal to pi r square equal to pi r 0.1 equal to 0.31. R should be given, and then we have this is Q conduction. So Q equal to Ka delta T over L, or delta X. L means thickness. So need to find what are the value of the other side. On the other side means outside here lah, what are the temperatures. So rearrange and put everything the value that you have here, and you have the outside value is 105.143. Alright, thank you very much.